Hello, dear friend, and welcome to this quiet corner of the cosmos where time moves slowly and wonder fills every breath. Tonight, I invite you to settle into the most comfortable space you can find. Let your shoulders drop and allow your mind to drift beyond the boundaries of our small world. We're about to embark on an extraordinary cosmic journey together, one that will take us through the most epic biography ever written. Tonight's story unfolds across 10 billion years, following the complete life cycle of a star from its birth in the dark depths of space to its final transformation into something entirely new. This isn't just any tale about distant suns. This is the story of how the very atoms that make up your body came to exist, forged in the nuclear hearts of ancient stars and scattered across the galaxy in acts of cosmic generosity. You are intimately connected to every moment of this stellar drama, literally made from the ashes of stars that lived and died long before our Earth was born. Our journey will unfold in gentle chapters, each one revealing a different phase of stellar life, from the patient collapse of cosmic clouds to the breathtaking beauty of planetary nebulae. Along the way, we'll discover how stellar death becomes the universe's greatest gift, creating the elements that make planets, oceans, and life itself possible. So close your eyes, friend, and let's begin this timeless voyage through the stars. Close your eyes and imagine time itself stretching like a vast, silent ocean before you. In your everyday life, a year feels substantial. Birthdays come and go, seasons turn their familiar wheel, and you measure your existence in decades. But tonight, we're going to step outside the boundaries of human time and enter a realm where a single breath spans millions of years, where youth lasts longer than entire civilizations, and where death becomes the most spectacular gift imaginable. We're going to follow the biography of a star, not just any star, but a star like our own sun, though each stellar life is as unique as a fingerprint written in plasma and light. This is a story that unfolds across billions of years, a narrative so grand that if human history were compressed into a single heartbeat, our star's life would stretch across countless lifetimes of heartbeats, each one marking eons of cosmic evolution. Picture yourself floating in the depths of space, not as an observer bound by flesh and time, but as consciousness itself, patient, eternal, capable of witnessing the slowest and most magnificent transformations in the universe. From this perspective, you'll watch as gravity sculpts matter, as nuclear fires ignite in the darkness, and as stellar winds carry the very elements that would one day form planets, oceans, and perhaps even life itself. The star we'll follow tonight represents roughly 90% of all stellar lives, neither the brief, explosive existence of massive giants nor the dim, eternal glow of tiny dwarfs, but something beautifully ordinary and extraordinarily long. Like a middle child of the cosmos, it will live a balanced life, neither too fast nor too slow, neither too bright or too dim. But what does it mean for a star to live? What does it mean for a bowl of gas to have a biography worth telling? A star's life is written in the language of nuclear fusion, in the delicate balance between the crushing inward pull of gravity and the explosive outward pressure of energy. It's a life measured not in breaths or heartbeats, but in the steady consumption of hydrogen, the gradual accumulation of helium ash, and the imperceptible changes in brightness and color that mark the passage of stellar seasons. Tonight, we'll witness birth in clouds so vast they dwarf solar systems, childhood that lasts longer than planets take to form, and a maturity so stable it could nurture life across geological ages. We'll see middle age bring subtle changes and growing instability. Old age transform our star into something almost unrecognizable. And finally, death that becomes not an ending but a spectacular rebirth, a cosmic gift that makes future stars, future planets, and perhaps future life possible. This is a story of patience on a scale almost impossible to comprehend. While galaxies spin and collide, while planets form and evolve and sometimes die, our star will maintain its steady nuclear heartbeat, converting 4 million tons of itself into pure energy every second. Yet changing so slowly that billions of human generations could pass without noticing any difference at all. Yet change it does. Deep in its core, where temperatures reach 15 million degrees and pressure compresses matter to densities beyond imagination. The star is constantly writing its own slow transformation. Each fusion reaction that converts hydrogen to helium leaves behind a tiny change, and across millions of years, these tiny changes accumulate into dramatic transformations. As we begin this journey, remember that you are intimately connected to this story. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were forged in the nuclear furnaces of stars that lived and died long before our sun was born. You are not merely observing this stellar biography. You are made of the same elements that will compose our star's ultimate legacy. So settle into this cosmic timescale. Let your human urgency dissolve into stellar patience, and prepare to witness one of the most beautiful and inevitable stories the universe has to tell, the life and death and rebirth of a star. Our story begins not in the brightness of stars, but in the darkness between them. Here, in the cold void where temperatures hover just a few degrees above absolute zero, vast clouds of gas and dust drift through space like cosmic fog. These are nebulae stellar nurseries, where baby stars are born from the remnants of previous generations. Picture the Orion Nebula, one of the most beautiful and active star-forming regions visible from Earth. If you could float through its gossamer structures, you would find yourself surrounded by hydrogen and helium gas so thin that the best vacuum chambers on Earth seem dense by comparison. Yet this seemingly empty space contains everything needed to build a star, matter, gravity, and time. The nebula where our star will be born spans dozens of light years, a distance so vast that light, traveling at 186,000 miles per second, would take decades to cross from one side to the other. Within this cosmic nursery, the gas isn't distributed evenly. Like cream slowly swirling in coffee, the matter has formed clumps and filaments, dense knots where gravity has begun its patient work of collection. Something triggers the collapse, perhaps the shock wave from a nearby supernova, like a cosmic stardust pistol signaling the beginning of stellar formation. Or maybe it's the gravitational influence of a passing star, gently disturbing the delicate equilibrium that has kept the gas clouds stable. Sometimes it's simply the slow accumulation of matter reaching a critical threshold where gravity finally overwhelms. The gas pressure that has resisted collapse. Whatever the trigger, once it begins, the process becomes inevitable. Gravity, the gentlest of all fundamental forces, begins to pull the gas and dust inward. At first, the collapse is imperceptibly slow over millions of years. The cloud begins to shrink and rotate, like a figure skater pulling in their arms during a spin. As our star-to-be continues to contract, something remarkable happens. The random motions of the gas particles begin to generate heat. This might seem counterintuitive. After all, we're used to thinking of space as cold, but temperature is really just a measure of how fast particles are moving. And as gravity compresses the gas, the particles collide more frequently and more violently. The center of our collapsing cloud begins to glow. First with infrared light invisible to human eyes, then with a dull red radiance. This is a protostar, not yet a true star, but no longer just a cloud. It's like cosmic adolescence, an awkward phase between what was and what will become. For the next few million years, our protostar continues to contract and heat up, fed by the steady infall of material from the surrounding nebula. Jets of hot gas shoot out from its poles like cosmic geysers, carving cavities in the surrounding dust and announcing to the universe that something significant is happening here. The protostar is surrounded by a disk of swirling matter, the same disk from which planets might eventually form. This disk glows with the heat of friction as particles spiral inward, their gravitational potential energy converting to thermal energy in a process that will one day be mimicked in computer. Hard drives and bicycle brakes across the cosmos. Deep in the core of our protostar, temperature and pressure continue to climb. 10,000 degrees becomes 100,000, then 1,000,000. The hydrogen nuclei, single protons, begin moving faster and faster, their thermal velocity increasing with the rising temperature. But they're still not fast enough or numerous enough to overcome the electrical repulsion that keeps atomic nuclei apart. This is one of the most critical phases in stellar birth. The protostar is like a cosmic engine trying to start on a cold morning. It has almost everything it needs to begin the nuclear fusion that will define its adult life, but not quite enough temperature and pressure to ignite the stellar fire. As millions of years pass, the core temperature climbs toward 10 million degrees Kelvin. At these temperatures, the hydrogen nuclei are moving at thousands of miles per second, fast enough that quantum mechanics begins to play a crucial role. Through a phenomena called quantum tunneling, some protons can overcome the electrical barrier that normally keeps them apart, allowing them to get close enough for the strong nuclear force to take over and bind them together. When four hydrogen nuclei finally combine to form one helium nucleus, something magical happens. The helium nucleus weighs slightly less than the four hydrogen nuclei that created it. That missing mass, just 0.7%, converts directly into energy according to Einstein's famous equation, E equals mc. Since the speed of light squared is an enormous number, even this tiny amount of missing mass produces tremendous energy. This is the moment of stellar ignition, the birth cry of a new star. The first fusion reactions generate enough heat and pressure to stop the gravitational collapse. For the first time in millions of years of steady contraction, the inward pull of gravity meets its match in the outward pressure of hot gas and radiation. The star has found its equilibrium, its nuclear heartbeat, the rhythm that will sustain it for billions of years to come. But this nuclear ignition doesn't happen all at once throughout the star. It begins in the core, where temperatures and pressures are highest, and gradually establishes a stable burning region. The star's core becomes a nuclear reactor, steadily converting hydrogen to helium and releasing energy that will take thousands of years to work its way from the interior to the surface. Our newborn star clears away the remaining gas and dust from its birth cloud like a cosmic sneeze. Stellar winds as streams of charged particles, flowing outward at millions of miles per hour, sweep the surrounding space clean. What was once a dark nebula becomes transparent, revealing the new star's light to the universe for the first time. The star has officially joined what astronomers call the main sequence, the long, stable phase of stellar adulthood that lies ahead. But even in these first moments of nuclear life, the star's ultimate fate is already written in its mass. Too little mass, and it will burn slowly and dimly for trillions of years. Too much mass, and it will live fast and die young in a supernova explosion. Our star, with just the right amount of mass, has found the sweet spot that will allow it to burn steadily for 10 billion years or more. As the stellar winds clear away the birth debris, planets may already be forming in the leftover disk of matter, rocky worlds close to the star, gas giants farther out, and perhaps, on one perfect world at just the right distance, the chemical ingredients for life itself. Our star has been born. Its childhood is about to begin. Picture a child's bedroom at night. Steady, predictable, comfortable. The nightlight glows with the same gentle warmth every evening, neither too bright nor too dim, creating a space where dreams can flourish and growth can happen at its own natural pace. Our newborn star has become the universe's most reliable nightlight, settling into what will be the longest and most stable phase of its existence. This is the main sequence, a cosmic childhood that will last for approximately 10 billion years. To put this timescale in perspective, imagine that our star's entire life is condensed into a single human lifetime of 80 years. Its main sequence phase would represent roughly 72 of those years, nearly 9 decades of steady, unchanging nuclear burning that provides the stable foundation for everything else to develop. During these early main sequence years, our star has achieved something remarkable. Perfect balance. Deep in its core, gravity pulls inward with relentless determination, trying to compress the star into a point. But the nuclear fusion reactions push outward with equal force, converting hydrogen to helium and releasing energy that creates the pressure needed to resist gravitational collapse. This equilibrium is called hydrostatic balance, and it's as delicate and beautiful as a dancer holding a perfect pose. Too little fusion and gravity would begin to compress the star, raising temperatures and increasing the fusion rate until balance is restored. Too much fusion, and the star would expand and cool until the nuclear fires calm down to sustainable levels. It's a cosmic thermostat, automatically adjusting to maintain stability. But what makes each star unique during this phase? Just as children develop distinct personalities, even in their earliest years, stars of different masses exhibit remarkably different characteristics during their main sequence lifetime. Massive stars burn bright and hot like cosmic teenagers, living fast and burning through their nuclear fuel at prodigious rates. They glow blue-white with surface temperatures exceeding 30,000 degrees Kelvin, and they consume their hydrogen so rapidly that their main sequence lifetime might last only a few million years, a cosmic blink of an eye. At the other extreme, red dwarf stars burn so slowly and efficiently that their main sequence phase could last for trillions of years, longer than the current age of the universe. These stellar marathoners convert their hydrogen with such miserly precision that some red dwarfs born shortly after the Big Bang are still in their stellar infancy today. Our star falls into the perfect middle ground. With a mass similar to our sun, it burns its nuclear fuel at a rate that allows for both stability and longevity. Its surface temperature settles at about 5,800 degrees Kelvin, giving it that familiar yellow-white glow that has become synonymous with the warmth of stellar light. During these early main sequence years, the star establishes its internal architecture. The core, where nuclear fusion occurs, occupies only about 25% of the star's radius, but contains 60% of its mass. Here, temperatures reach 15 million degrees and pressures exceed 200 billion times Earth's atmospheric pressure. In this cosmic pressure cooker, hydrogen nuclei move fast enough to overcome their electrical repulsion and fuse into helium. The energy produced in the core begins a remarkable journey to the surface. Unlike the few minutes it takes sunlight to travel from the sun to Earth, the energy created in stellar cores can take thousands of years to work its way outward. Photons of light are absorbed and re-emitted countless times as they random walk through the dense stellar interior, gradually cooling from high-energy gamma rays to the visible light that eventually illuminates space. Surrounding the core is the radiative zone, where energy travels primarily through electromagnetic radiation. Above that lies the convective zone, where hot gas physically rises to the surface, cools, and sinks back down in enormous circulation patterns. These convection cells are like cosmic lava lamps, constantly churning and mixing the star's outer layers. During this long childhood phase, our star's surface shows the signs of this internal activity. Dark spots appear and disappear as magnetic field lines become tangled in the convective flows. Solar flares erupt when these magnetic fields suddenly reconnect, releasing stored energy in brilliant displays of stellar plasma. These surface features are like cosmic acne, temporary blemishes that mark the star's active youth. The stellar winds during this phase are relatively gentle, a steady breeze of charged particles, flowing outward at speeds of a few hundred miles per second. These winds carry the star's magnetic field throughout its stellar system, creating a bubble of influence called the heliosphere that extends far beyond any planets that might orbit the star. If planets have indeed formed around our star, this is the phase when life might first emerge on any worlds that happen to lie within the habitable zone, that perfect distance where liquid water can exist on a planet's surface. The star's steady, predictable energy output creates the stable environment necessary for the slow chemistry of biological evolution. From the perspective of any hypothetical observers on such a planet, the star would appear remarkably constant. Its brightness might vary by tiny amounts due to the rotation of spots and the 11-year cycle of magnetic activity. But overall, it would provide the steady illumination that complex ecosystems require. Yet even during this stable phase, subtle changes are occurring deep within the star's core. Each fusion reaction converts four hydrogen nuclei into one helium nucleus, gradually changing the composition of the core region. As millions of years pass, the percentage of hydrogen decreases while helium accumulates like ash in a cosmic fireplace. This helium accumulation doesn't affect the star's appearance or behavior during its early main sequence years, but it's slowly changing the core's properties. Helium nuclei are heavier than hydrogen nuclei, so the core gradually becomes denser. This increased density requires slightly higher temperatures to maintain the same fusion rate, causing the star's energy output to increase very gradually over time. The changes are so slow that they're imperceptible on human time, but they're nevertheless writing the first chapter of the star's eventual evolution away from the main sequence. like the gradual graying of hair or the slow accumulation of wisdom. These changes mark the passage of stellar time in ways that only become apparent when viewed across millions of millennia. For now, though, our star shines with the steady confidence of youth. It has found its rhythm, established its nuclear heartbeat, and settled into the long, patient work of converting hydrogen to helium while providing light and warmth to its corner of the galaxy. The stellar childhood will continue for billions of years, but already, in these early phases of main sequence life, the stage is being set for all the dramatic changes that lie ahead. The helium ash accumulating in the core, the gradual brightening, the steady aging of nuclear fuel. These subtle transformations will eventually trigger the star's first major life transition, but that transition is still eons in the future. For now, our star burns with the eternal optimism of youth, steady and bright and seemingly unchanging. A cosmic lighthouse guiding any observers through the long night of space. 5 billion years have passed, a span of time so vast that if each year were a grain of sand, the beach would stretch from New York to Los Angeles. Our star has burned through roughly half of the hydrogen fuel in its core, and subtle changes are beginning to accumulate, like the first gray hairs or the gradual stiffening of once flexible joints. If you could peer into the star's core with cosmic X-ray vision, you would see that it no longer looks quite the same as it did during those early main sequence years. The nuclear furnace that once burned pure hydrogen now contains a growing heart of helium, the ash of billions of years of fusion reactions. This helium core sits inert at the center of the star. Too cool to ignite its own fusion reactions, but dense enough to begin affecting everything around it. Think of this helium accumulation like sediments settling at the bottom of a cosmic river. Each helium nucleus created by fusion is heavier than the hydrogen from which it formed, so it tends to sink toward the star's center under the influence of gravity. Over billions of years, this process has created a distinct core of helium surrounded by a shell of hydrogen that continues to undergo fusion. The presence of this helium core subtly changes the star's internal balance. Because helium doesn't participate in fusion at the relatively low temperatures of stellar cores, the core becomes less efficient at generating the pressure needed to support the weight of the overlying layers. To compensate, the surrounding hydrogen-burning shell must work slightly harder, burning at a higher rate to maintain hydrostatic equilibrium. This increased fusion rate causes the star to grow gradually brighter over millions of years. The change is so slow that it's imperceptible in human timescales, perhaps a 1% increase in brightness every 100 million years. If Earth orbited this star, the climate changes would be subtle but inexorable, like the slow warming that comes with the approach of summer, but stretched across geological ages. As our star continues to age, the helium core grows larger and more massive. Like a cosmic snowball, it accumulates more helium with each passing million years, becoming an increasingly significant factor in the star's internal structure. The hydrogen-burning shell that surrounds this core must maintain higher and higher temperatures and pressures to support the growing weight of helium ash. During this middle age phase, the star's surface begins to show the first signs of internal changes. Its spectrum, the rainbow of colors contained in its light, shifts subtly as the increased core temperature affects the nuclear reaction rates. Sensitive instruments might detect minute variations in the star's oscillations, like a cosmic seismograph picking up tremors from deep within the stellar interior. These stellar oscillations are caused by sound waves propagating through the star's interior, a phenomenon called just as geologists study earthquake waves to understand Earth's internal structure, astronomers can analyze these stellar vibrations to peer inside stars and track their evolution. The star has become a cosmic musical instrument. Its changing internal structure, altering the fundamental frequencies of its oscillations. The magnetic field generated by the star's convective motions may also begin to change during this phase. The growing helium core and the increased energy output from the surrounding hydrogen shell can affect the convection patterns in the star's outer layers, potentially altering the strength and structure of its magnetic field. Solar spots and flares might become more or less frequent, and the stellar wind might strengthen or weaken in response to these magnetic changes. Yet from the outside, these changes remain largely invisible. To any civilizations that might have evolved on planets orbiting this star, it would still appear stable and reliable. The gradual brightening would be offset by the natural evolution of planetary atmospheres and the adjustment of life to slowly changing conditions. Stars in their middle age are still excellent suns for supporting complex ecosystems. But deep inside, a cosmic clock is ticking. As the helium core continues to grow, it eventually reaches a critical mass where its own gravity begins to compress it significantly. Unlike the hydrogen-burning shell above it, the helium core cannot release energy through fusion, so it has no way to generate the pressure needed to resist gravitational compression. It begins to contract under its own weight, like a cosmic balloon losing air. This contraction causes the helium core to heat up, even though no fusion is occurring within it. The increased temperature at the base of the hydrogen-burning shell causes the nuclear reactions there to proceed even faster, making the star burn brighter and begin to swell slightly. It's as if the star is developing cosmic middle-age spread, a gradual expansion that mirrors the core, contraction happening deep within. During these later middle-age years, roughly 8 to 9 billion years into the star's main sequence lifetime, the changes begin to accelerate. The helium core represents an increasingly large fraction of the star's total mass, and its gravitational influence becomes harder to ignore. The hydrogen-burning shell becomes thinner but more active, like a cosmic pressure cooker working overtime. The star's luminosity continues to increase, perhaps reaching 150% or 200% of its original brightness. Its surface temperature may decrease slightly as the star swells, giving it a subtly more orange or red appearance. These changes remain gradual by human standards, but represent significant evolution. If our star has planets, this is the phase when the inner worlds begin to experience more dramatic climate changes. Any terrestrial planets in what was once the habitable zone might start to overheat as the star's increasing brightness makes their surfaces too hot for liquid water. The habitable zone itself begins to migrate outward, potentially bringing previously frozen worlds into the realm where life could exist. Meanwhile, the stellar wind may begin to strengthen as the star's increased luminosity drives more particles from its surface. The heliosphere, the bubble of solar influence surrounding the star, might expand, affecting the space environment around any orbiting planets. Throughout this middle-age phase, our star remains fundamentally stable. The hydrogen fusion in the shell surrounding the helium core continues to provide the energy needed to balance gravity's inward pull. The star has not yet reached the point where dramatic structural changes become inevitable, but those changes are approaching, like a middle-aged person beginning to feel the first signs that their body won't stay young forever. The star is showing subtle symptoms of the dramatic transformation that lies ahead. The helium core continues to grow. The hydrogen shell burns ever more frantically, and the star's luminosity climbs steadily toward the threshold that will trigger its next major evolutionary phase. For now, though, the star continues its patient work of nuclear alchemy, converting hydrogen to helium and providing steady energy to its corner of the cosmos. It has been a reliable sun for nearly its entire 10 billion year lifetime, and it will continue to shine steadily for perhaps another billion years. But the cosmic clock continues to tick, and the helium core continues to grow, and somewhere in the star's future, a moment of dramatic change is waiting. The transition from middle age to stellar elderhood is approaching, bringing with it transformations that will reshape everything about this star's appearance, behavior, and ultimate destiny. The long, stable childhood and middle age of stellar life are drawing toward their close, and the most spectacular chapters of our star's biography are about to begin. Imagine watching a time-lapse video of a flower blooming, but stretched across hundreds of millions of years. What begins as a gradual swelling becomes a dramatic transformation as our star enters the most visually spectacular phase of its life. The helium core that has been growing quietly for billions of years finally reaches a critical threshold, triggering changes that will remake the star from the inside out. 10 billion years have passed since nuclear fusion first ignited in the star's core. The helium ash that has accumulated there now represents nearly 40% of the star's total mass, compressed into a region smaller than Earth but containing more matter than hundreds of Earths combined. This helium core has become so dense that the electrons have been squeezed into a strange state of matter called electron degeneracy, a quantum mechanical condition where the normal rules of gas pressure no longer apply. In this degenerate state, the helium core can no longer expand to relieve pressure. Even as it continues to heat up from the gravitational compression and the energy flowing down from the hydrogen-burning shell above, it's like trying to compress a steel ball with your bare hands beyond a certain point. The material simply refuses to give way, no matter how much force is applied. This resistance to compression causes the core temperature to rise rapidly, heating the base of the hydrogen-burning shell to temperatures and pressures far higher than anything the star experienced during its main sequence lifetime. The shell responds by burning hydrogen at a furious rate, releasing energy at levels that dwarf the star's previous output. But here's where stellar evolution becomes counterintuitive. Instead of making the star brighter and hotter on the surface, this increased energy output causes the star's outer layers to expand dramatically. It's like inflating a cosmic balloon as more energy flows outward from the core. The star's atmosphere swells to dimensions that would have seemed impossible during its main sequence years. Over the course of just a few million years, rapid by stellar standards, our star's radius increases by factors of 10, 50, or even 100 times its original size. If this star were our sun, its surface would expand beyond the orbit of Mercury, then Venus, possibly reaching nearly to Earth's orbit. The same amount of matter that once fit within a sphere roughly the size of our sun now occupies a volume larger than Earth's entire orbit. This expansion has a remarkable effect on the star's surface temperature. Even though the core is burning hotter than ever before, the enormous surface area causes the star's outer layers to cool significantly. The surface temperature drops from its main sequence value of nearly 6,000 degrees to perhaps 3,500 or 4,000 degrees Kelvin. This cooling shifts the star's color from yellow-white to orange or deep red, giving rise to the term red giant. The transformation is breathtaking to imagine. A star that once shone with the bright, steady light of a cosmic lighthouse now glows with the deep, ruddy radiance of a stellar campfire. Its luminosity increases dramatically, perhaps 1,000 times brighter than it was during its main sequence years. But this light is now spread across an enormous surface area and dominated by longer, redder wavelengths. From the perspective of any planets that might orbit this star, the changes are nothing short of apocalyptic. The star's habitable zone migrates outward as its luminosity increases, potentially bringing distant, previously frozen worlds into the realm where liquid water could exist. But any inner planets face a far more dramatic fate. As the star's atmosphere expands, it may literally engulf the inner worlds. Planets that once orbited safely millions of miles from the stellar surface now find themselves plowing through the star's extended atmosphere. The friction from this interaction causes the planets to spiral inward, their orbits decaying as they lose energy to atmospheric drag. Eventually, these worlds are consumed entirely, their matter mixed into the star's outer layers. Even planets that avoid direct engulfment face intense radiation and stellar winds far stronger than anything they experienced during the star's main sequence years. Atmospheres are stripped away, oceans boil, and any life that might have evolved during the star's stable phase is likely extinguished. The red giant phase represents a cosmic changing of the guard, erasing much of what came before and setting the stage for whatever comes next. But the red giant phase is not simply destructive. The intense stellar winds generated during this period, perhaps 1,000,000 times stronger than the gentle breezes of the main sequence years, begin to enrich the surrounding space with heavy elements forged in the star's interior. Carbon, nitrogen, oxygen, and other elements crucial for planet formation and life are carried outward on these winds, eventually mixing with the interstellar medium and becoming available for future generations of stars and planets. The stellar interior during this phase becomes increasingly complex, with multiple layers burning different fuels at different rates. The degenerate helium core continues to heat up from gravitational compression, while the hydrogen-burning shell above it works frantically to support the star's enormous luminosity. Above that, vast convection cells circulate material between the core region and the star's surface, occasionally dredging up elements from the interior and bringing them to the surface where they can be detected in the star's spectrum. As millions of years pass, the helium core continues to compress and heat up. approaching the temperature threshold where helium itself can begin to fuse. When the core temperature reaches about 100 million degrees Kelvin, nearly 7 times hotter than the hydrogen-burning core during the main sequence, something remarkable happens. 3 helium nuclei combine in a process called the triple alpha reaction, forming a carbon nucleus and releasing energy. But helium fusion is far more sensitive to temperature than hydrogen. Fusion. A small increase in temperature causes a dramatic increase in the fusion rate. In the degenerate matter of the core, where normal gas pressure relationships don't apply, this temperature sensitivity leads to a runaway reaction. The helium flash occurs over the course of just a few seconds, faster than sound waves can travel through the star's interior. In those brief moments, the core releases as much energy as the entire star normally produces in thousands of years. It's like a cosmic hiccup, a stellar sneeze that briefly produces more energy than entire galaxies. Remarkably, this enormous energy release is almost entirely invisible from the outside. The helium flash occurs so deep within the star and is absorbed so completely by the overlying layers that the star's surface brightness barely changes. Only sensitive seismic observations might detect the sound waves generated by this dramatic internal event. The helium flash breaks the degeneracy in the core, allowing it to expand and establish a new equilibrium. For the first time in millions of years, the core can generate its own pressure through nuclear fusion, taking some of the burden off the hydrogen-burning shell. The star contracts somewhat from its maximum red giant size and enters a new phase of stability. But this is only a temporary reprieve. The helium in the core will eventually be exhausted, just as the hydrogen was before it. The star has gained a few 100 million years of stable burning, but the fundamental problem remains. It's running out of nuclear fuel that can burn at the temperatures and pressures available in stellar cores. As our red giant settles into this new equilibrium, burning helium in its core and hydrogen in a shell above, it has already written much of its legacy across space. The heavy elements carried outward by its stellar winds are spreading through the local interstellar medium, enriching the raw material from which future stars will form. Any planets that survived the red giant expansion have been fundamentally altered, their surfaces and atmospheres transformed by the star's intense radiation and wind. The star has become a cosmic alchemist, transforming simple hydrogen into the complex elements that make rocky planets, organic molecules, and perhaps even life possible. This transformation comes at a cost. The star's days as a stable, long-lived source of energy are numbered. But in exchange, it has begun to give back to the universe the gifts of chemical complexity and elemental diversity that will benefit countless future generations of cosmic evolution. The red giant phase represents the beginning of the end, but also the beginning of the star's greatest gift to the cosmos. The transformation from stable main sequence star to red giant marks the moment when our star stops being merely a consumer of hydrogen and becomes a creator and distributor of the elements that make complexity possible in the universe. The final act of our star's Timbiliar drama unfolds. With the inexorable logic of physics and the breathtaking beauty of cosmic transformation, after hundreds of millions of years as a red giant, burning helium in its core and hydrogen in a surrounding shell, our star faces the ultimate challenge that all stars must eventually confront. It is running out of nuclear fuel that can sustain it against the relentless inward pull of gravity. Deep within the star's core, the helium fusion reactions that provided temporary stability are creating their own form of ash, carbon, and oxygen nuclei that accumulate, just as helium once accumulated during the main sequence years. But unlike the transition from hydrogen to helium burning, there will be no reprieve this time. Our star simply doesn't have enough mass to compress its core to the temperatures needed for carbon fusion, which requires nearly 1 billion degrees Kelvin. As the helium in the core becomes depleted, the same pattern repeats that we saw at the end of the main sequence phase. The carbon-oxygen core begins to contract under its own gravity, heating up but unable to ignite fusion reactions. This contraction causes the helium-burning shell above it to burn more intensely, which in turn affects the hydrogen-burning shell even farther out. The star's internal structure now resembles a cosmic onion, with multiple layers burning different fuels at different rates. At the center sits the inert carbon-oxygen core, surrounded by a helium-burning shell, which is surrounded by a hydrogen-burning shell, all wrapped in the enormous, extended atmosphere that gives the red giant its distinctive appearance. But this complex structure is inherently unstable. The multiple burning shells interact with each other in chaotic ways, causing the star's energy output to become erratic. Sometimes the shells burn quietly and steadily. Other times they ignite in brief, intense bursts that send pulses of energy rippling through the star's atmosphere. These thermal pulses create one of the most beautiful phenomena in stellar evolution. Each pulse drives shock waves through the star's extended atmosphere, heating and accelerating the stellar wind to velocities of tens of miles per second. The enhanced stellar wind carries away enormous amounts of matter, perhaps 50% or more of the star's total mass during this phase. As this mass loss continues over thousands of years, something remarkable begins to happen. The star's extended red giant atmosphere is gradually stripped away, revealing the hot, dense core region beneath. It's like watching a cosmic strip as layer after layer of the star's outer atmosphere is carried away on the stellar wind, exposing the nuclear furnace that has been hidden within. The ejected material doesn't simply vanish into space. Instead, it forms an expanding shell of glowing gas around the star, a planetary nebula. Though it has nothing to do with planets, the name comes from early telescopic observations, when these circular, disk-like objects resembled the appearance of distant planets through small telescopes. These planetary nebulae are among the most beautiful objects in the universe. The hot, exposed core of the dying star, now called a white dwarf, emits intense ultraviolet radiation that causes the surrounding shell of ejected material to fluoresce like a cosmic neon sign. Different elements glow with different colors. Hydrogen produces red light, oxygen glows green and blue, and nitrogen adds touches of red and purple to the mix. The result is a breathtaking display of cosmic artistry. Some planetary nebulae look like perfect spheres of glowing gas. Others resemble hourglasses, butterflies, or eyes looking back at us from across space. Each one is unique, shaped by the complex interplay between stellar winds, magnetic fields, and the three-dimensional structure of the ejected material. But the true protagonist of this final act is not the beautiful nebula, but the small, hot star at its center. This white dwarf represents the exposed core of our once mighty red giant, a sphere about the size of Earth, but containing roughly 60% of the original star's mass. It's made primarily of carbon and oxygen nuclei in a sea of degenerate electrons, compressed to densities so extreme that a teaspoon of white dwarf material would weigh as much as a car. When our star first becomes a white dwarf, its surface temperature may exceed 100,000 degrees Kelvin, nearly 20 times hotter than the sun's surface. This extreme temperature is what provides the ultraviolet radiation needed to ionize and illuminate the surrounding planetary nebula. The white dwarf glows with a brilliant blue-white light, more luminous than our sun despite being much smaller. But unlike every previous phase of stellar evolution, the white dwarf generates no new energy through nuclear fusion. It shines solely by radiating away the tremendous heat stored within its compressed matter. This means that from the moment of its formation, the white dwarf begins a slow, inexorable process of cooling that will continue for billions upon billions of years. The cooling happens gradually, following the laws of thermodynamics with mathematical precision. Over millions of years, the white dwarf's surface temperature drops from 100,000 degrees to 50,000, then 20,000, then 10,000. Its color changes from brilliant blue-white to white, then to yellow, orange, and eventually to red. As it cools, it also grows dimmer, fading from a brilliant beacon to a dim ember. Meanwhile, the planetary nebula continues to expand outward at speeds of tens of miles per second. Over thousands of years, it grows from a compact shell around the white dwarf to a gossamer bubble of glowing gas, several light years across. But as it expands, it also becomes more diffuse, and the white dwarf's cooling surface can no longer provide enough ultraviolet radiation to keep the nebula glowing. After perhaps 10,000 to 50,000 years, the planetary nebula fades from view, its material now mixed with the general interstellar medium. What remains is a solitary white dwarf, cooling slowly in the darkness of space like a cosmic ember gradually losing its warmth. The white dwarf cooling process is almost unimaginably slow. After a billion years of cooling, the white dwarf might still have a surface temperature of several thousand degrees, hot enough to glow with a dull red light. After 10 billion years, longer than the current age of the universe, it might still be warm enough to emit faint infrared radiation. Eventually, after trillions of years, the white dwarf will cool to the temperature of the surrounding space and become a cold, dark object called a black dwarf. But this final phase is so far in the future that no black dwarfs yet exist anywhere in the universe. The cosmos simply hasn't been around long enough for even the oldest white dwarfs to cool completely. For our star, this represents the end of active evolution. The white dwarf phase is a cosmic retirement, a long, slow fade into darkness that will outlast the evolution of galaxies, the formation and death of countless future generations of stars, and perhaps even the eventual expansion and cooling of the universe itself. But stellar death is not the end of the story. Throughout its red giants and planetary nebula phases, our star has been performing its greatest act of cosmic generosity. The carbon and oxygen forged in its core, the nitrogen created by nuclear processing in its interior, and even some of the original hydrogen and helium from its birth, all of these elements have been scattered into space by stellar winds and the eventual ejection of the planetary nebula. These elements now drift through the interstellar medium, mixing with gas from other dying stars and waiting to be incorporated into the next generation of stellar and planetary formation. The carbon atoms might become part of organic molecules in a distant world. The oxygen might form water in a planet's ocean. The nitrogen might become part of the atmosphere where life evolves. In this way, our star's death becomes a gift to the future. It has transformed simple hydrogen and helium into the complex elements that make rocky planets, organic chemistry, and biological evolution possible. It has served as a cosmic alchemist, using nuclear fusion to transmute the basic building blocks of matter into the diverse palette of elements that gives the universe its richness and complexity. As the white dwarf continues its billion-year cooling process, and as the elements it once created spread throughout the galaxy, our star's legacy lives on. It may no longer burn with nuclear fire, but its contribution to cosmic evolution will continue for eons to come, written in the very atoms that make up future worlds and perhaps future life. The biography in our star is complete, but its story continues in every atom it created, in every world that might someday form from its scattered remains. In the vast theater of space, where our star once shone as a bright protagonist, a more subtle drama now unfolds. The white dwarf continues its slow cooling in solitude, but the real action has moved to the expanding shell of gas and dust that was once the star's outer atmosphere. This material, enriched with elements forged in the stellar interior, begins its journey toward becoming the foundation for new generations of cosmic evolution. Picture the aftermath of a cosmic fireworks display, where the brilliant explosion has faded, but the glowing embers continue to drift outward, carrying their light into previously dark corners of space. The planetary nebula phase represents just the beginning of this dispersal process. Over hundreds of thousands of years, the shell of ejected stellar material continues to expand and cool, gradually mixing with the existing interstellar medium. This mixing process is one of the most important mechanisms by which the galaxy enriches itself with heavy elements. When our star was born 10 billion years ago, the surrounding interstellar medium consisted almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. But now, as the stellar ejecta spreads through space, it carries carbon, nitrogen, oxygen, and traces of many other elements that simply didn't exist in significant quantities when the first stars formed. Each cubic light year of space touched by our star's expanding shell becomes slightly more metal, to use the astronomical term for any element heavier than hydrogen and helium. This enrichment may seem insignificant, perhaps the abundance of heavy elements increases by only a few parts per million. But across the vast scales of galactic evolution, these tiny increments accumulate into the chemical complexity that makes rocky planets and organic chemistry possible. The carbon atoms forged in our star's helium-burning core are now free to participate in the rich chemistry of interstellar space. Some will form simple molecules like carbon monoxide, which can be detected by radio telescopes as it emits characteristic frequencies of microwave radiation. Others might become part of more complex organic molecules, the precursors to amino acids, sugars, and other biological building blocks that can form even in the cold vacuum of space. The oxygen created alongside the carbon will also begin new chemical adventures. Much of it will remain in atomic form, eventually ionized by the ultraviolet radiation from young, hot stars. But some will combine with hydrogen to form water molecules, or with carbon to create carbon monoxide and carbon dioxide. These simple molecules become the raw materials from which planetary atmospheres and oceans can eventually form. As millions of years pass, the expanding shell of stellar material encounters other structures in the interstellar medium. It might collide with gas clouds, shocking and compressing them in ways that can trigger new episodes of star formation. It might interact with the stellar winds from other nearby stars, creating complex patterns of turbulence and density variations that shape the evolution of the local galactic environment. Meanwhile, other stars throughout the galaxy are undergoing their own life cycles, each contributing its own unique mixture of elements to the cosmic recycling process. Massive stars, which live fast and die young in spectacular supernova explosions, add their own complement of heavy elements, including iron, nickel, and other metals that form in the extreme conditions of stellar core collapse. Over billions of years, this ongoing process of stellar birth, evolution, death, and material recycling gradually transforms the chemical composition of entire galaxies. The Milky Way today contains roughly 2% heavy elements by mass, a small percentage, but one that represents the accumulated nuclear alchemy of hundreds of billions of stellar life cycles over the past 13 billion years. But the most remarkable chapter of this recycling story comes when the enriched interstellar medium begins to collapse and form new stars. Imagine a molecular cloud, one of those vast, cold nurseries where stars are born, but now containing not just hydrogen and helium, but also carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements created in the cores of previous stellar generations. When such an enriched cloud begins to collapse under its own gravity, something new becomes possible. The heavy elements, though still representing only a tiny fraction of the total mass, can condense into solid grains of dust. These dust particles serve as nucleation sites where more complex materials can accumulate, eventually growing into the rocky building blocks of planets. A second-generation star forming from this enriched material may develop not just a nuclear burning core, but also a surrounding disk of gas and dust that contains the ingredients for terrestrial planets. Rocky worlds can form from the silicon, magnesium, iron, and other heavy elements. Icy comets can condense from water, methane, and ammonia in the cooler outer regions of the system. And on at least one of these rocky worlds, if conditions are exactly right, the carbon, nitrogen, oxygen, and other elements created in stellar cores can participate in an even more remarkable process, the chemistry of life itself. This is perhaps the most profound aspect of stellar evolution, the recognition that every atom in your body, except for hydrogen, was forged in the nuclear furnace of a star that lived and died long before our solar system formed. The calcium in your bones was created in the dying moments of a massive star's supernova explosion. The iron in your blood was synthesized in stellar cores over billions of years. The carbon that forms the backbone of every organic molecule in your body was manufactured in the helium burning phase of red giant stars. You are not merely an observer of stellar evolution, you are its direct product. A complex arrangement of stellar ashes that has somehow achieved consciousness and the ability to contemplate its own cosmic origin. When you look up at the night sky, you are quite literally seeing your ancestral home, the stellar forges where the elements of your being were created. But this cosmic recycling process is not a one-way street. The star whose life cycle we have followed will eventually be joined by our own sun and every other star currently shining in the galaxy. Each will contribute its own unique chemical signature to the ongoing enrichment of the interstellar medium. Each will add its voice to the great cosmic symphony of stellar evolution that has been playing for billions of years and will continue for billions more. The white dwarf that represents our star's final evolutionary state will continue cooling for trillions of years, long after the sun has gone through its own red giant phase and shed its outer layers into space. The galaxy itself will continue evolving, merging with other galaxies, forming new generations of stars from ever more chemically enriched material. Eventually, perhaps a trillion years from now, the era of star formation will end as the universe expands and cools beyond the point where molecular clouds can collapse and ignite nuclear fusion. But even then, the white dwarf remnants of stars like ours will continue to cool slowly in the darkness, the last glowing embers of an age when the universe was young and full of light. In this vast cosmic perspective, our star's 10 billion year lifetime represents just one verse in an epic poem that began with the Big Bang and will continue until the universe itself reaches thermal equilibrium. Yet within that brief stellar lifetime, something remarkable happened. Simple hydrogen was transformed into complex elements. Stable energy was provided to nurture planetary evolution, and the chemical foundations were laid for the emergence of complexity, chemistry, and perhaps even consciousness. The star's death was not an ending, but a transformation, a cosmic metamorphosis that converted stellar mass into the building blocks of future worlds and future possibilities. In losing its life, the star gained a form of immortality, written not in light and heat, but in every atom of every world that will ever form from its scattered remains. As our journey through stellar time comes to a close, take a moment to let your awareness return to the present moment, to the brief flicker of time that represents your own existence within this vast cosmic story. The 10 billion years we have witnessed, from the collapse of a molecular cloud to the final cooling of a white dwarf, encompass a span so immense that human language struggles to contain it. Yet here you are, a conscious being capable of contemplating stellar events, made entirely of elements that were created in the nuclear furnaces of stars that lived and died long before our solar system existed. This is perhaps the most beautiful paradox of cosmic evolution, that the universe has become capable of understanding itself through the emergence of conscious observers made from its own stellar products. Think about the extraordinary journey that brought you to this moment of understanding. 13.5 billion years ago, the universe began with the simplest possible ingredients: energy, space, time, and the fundamental particles that would eventually become protons, neutrons, and electrons. For the first few 100 million years, no stars existed. The cosmos was dark, filled only with hydrogen and helium gas slowly cooling and condensing under the influence of gravity. The first stars that formed were different from the one whose life we have followed. They contained almost no heavy elements because no previous generations of stars had existed to create them. These early stellar giants lived fast and died violently, exploding as supernovas and seeding space with the first carbon, oxygen, silicon, and iron atoms the universe had ever known. Billions of years of stellar evolution followed, each generation of stars adding its own contribution to the slowly increasing abundance of heavy elements in the galaxy. Somewhere in this vast chain of stellar birth and death, the specific atoms that would eventually become part of your body were forged in stellar cores, accelerated in the supernova shock waves, and dispersed into the interstellar medium. 4.5 billion years ago, a particular molecular cloud enriched by countless previous generations of stellar evolution began to collapse under its own gravity. This cloud contained just enough heavy elements to allow the formation of rocky planets around the star that would become our sun. On one of these rocky worlds, at just the right distance from its star, the stellar products of carbon, nitrogen, oxygen, and countless other elements began to participate in increasingly complex chemistry. The rest, as they say, is history, though it's a history written in stellar nucleosynthesis, planetary formation, geological evolution, and ultimately biological evolution. Every breath you take contains oxygen atoms forged in stellar cores. Every thought you think involves carbon-based molecules created in the helium-burning shells of red giant stars. The calcium that gives strength to your bones, the iron that carries oxygen in your blood, the phosphorus that stores energy in your cells. All of these elements are gifts from stars that died before the Earth was born. This cosmic perspective offers a profound reframe for how we understand our place in the universe. We are not separate from the cosmos, observing it from some external vantage point. We are the cosmos becoming self-aware, the universe developing the capacity to study and understand itself through the emergence of conscious beings made from stellar ashes. When you look up at the night sky and see the light of distant stars, you are witnessing the same nuclear processes that created the elements of your own body. The fusion reactions burning in stellar cores throughout the galaxy are continuing the ancient work of elemental creation that made your existence possible. Every star you see is a nuclear furnace, patiently converting hydrogen to helium and slowly building the periodic table one fusion reaction at a time. This understanding can fundamentally change how we experience our daily lives. The morning sunrise carries light generated by nuclear fusion in our star's core, the same process that created much of the oxygen you breathe and the carbon in your DNA. The ground beneath your feet contains silicon, aluminum, and iron forged in stellar cores billions of years ago. Even the water you drink is made from hydrogen that dates back to the Big Bang and oxygen created in stellar nucleosynthesis. We are living in the golden age of stellar evolution, when the universe is old enough to have created complex elements through billions of years of stellar alchemy, but young enough that stars continue to shine throughout the galaxy. This is a brief and special time in cosmic history, when stellar light illuminates the darkness and provides the stable energy needed for complex chemistry and biological evolution. But our cosmic perspective also reminds us of the deep timescales on which stellar evolution operates. The star whose life we have followed maintains stable nuclear burning for 10 billion years, 1,000 times longer than complex life has existed on Earth. This stability across such vast timescales is what makes stellar evolution so remarkable and what has allowed complex systems like planets, atmospheres, and living organisms to develop. Yet even stars are not eternal. The white dwarf that represents our star's final state will cool for trillions of years, but eventually even this last vestige of stellar fire will fade into the darkness. New stars continue to form throughout the galaxy, but the raw materials for star formation are finite. Eventually, perhaps a trillion years from now, the last star will burn out, and the universe will enter a new phase where stellar light no longer illuminates the cosmic darkness. This far future reminds us that our current moment, when stars shine, when planets orbit stable suns, when life can emerge and evolve and contemplate its own existence, represents a brief and precious chapter in the universe's long story. We are fortunate to exist during this golden age of cosmic evolution, when stellar nucleosynthesis has created the elements needed for complexity. But stellar fuel still burns brightly throughout the galaxy. As you drift towards sleep tonight, carry with you this profound connection to stellar evolution. You are made of star stuff, literally and completely. Your existence represents the universe's extraordinary journey from simplicity to complexity, from hydrogen and helium to the periodic table of elements, from stellar cores to planetary surfaces to the remarkable chemistry of life and consciousness. In contemplating the life cycle of stars, we discover not just the physics of nuclear fusion and stellar evolution, but our own deepest origins and our intimate connection to the cosmic story that began with the Big Bang and continues unfolding around us every day. We are all children of stars, temporary arrangements of stellar products, brief witnesses to the ongoing epic of cosmic evolution. The universe continues to whisper its stories through every ray of starlight, every distant galaxy, and every cosmic phenomenon waiting to be understood. These tales of time and space are written in the language of physics and painted across the canvas of night, each one revealing another chapter in our ongoing journey of cosmic discovery and wonder. Sleep peacefully now, knowing that you carry within you the ancient light of stars, the memory of cosmic birth, and the promise of infinite tomorrows. Until we meet again in the vast cathedral of space and time, may your dreams be filled with stardust and wonder.